All right, so now we're going to work on basically what the second derivative test is a little bit. We're going to be looking at the second derivative now instead of the first derivative because it gives us a little bit more information. If the second derivative is less than zero, or sorry, greater than zero, meaning it's positive, that tells us that the graph is concave up, means it opens up like that. If the second derivative is less than zero, that means that the graph is concave down or opens down like that. So what's important to see about that is that we're going to have to figure out where the second derivative is equal to zero and test before and after that. And when the second derivative is actually equal to zero, okay, and so it's equal to zero and there's a sign change, okay, it could be equal to zero but no sign change. But if it is equal to zero and there's a sign change, that means we have a point of inflection. So those are the things that we're trying to test. This thing right here, this spot right here, is a point of inflection. And the reason I know that is because this is my original function, right? And I can see that this part of the function right here is concave down, and concave down would mean that it would be negative at that spot. And this point here, this section here, is concave up, so that would be positive at that point. And that's if I was looking at the second derivative. So there's your sign change, and the second derivative at this spot would equal zero because it would be, it would tell me that the first derivative was at a minimum because we're talking about the slope of this line. So what happens to the slopes of these tangent lines is we start at zero, and then as we move along this graph, the slopes are negative until we reach this point of inflection where it becomes the most negative, and then it starts flattening back out again. So what that tells me is that point right there, the tangent line right there, has the minimum or the most negatively sloped line. If I was heading the other direction, let's say I came down like this, right? This point right here would have the largest slope. So that would also be a point of inflection because it would have the largest slope, which means the first derivative would equal zero, and it would be changing from concave up to concave down. Okay, so we're going to apply this information to the examples we looked at the very beginning. I've already copied over the first derivative, the work we did to find the first derivative. And so what we're going to do is we're going to apply the second derivative and figure out which intervals the x's are concave up and which intervals make the graph concave down, and we're going to identify inflection points. Okay, so my first job is to find the second derivative and then set it equal to zero. Okay, so this one's not so bad. I want a different color ink here. So the second derivative in this case would equal, well, there's my first derivative, right? So it's going to be 12x minus 6. And now I'm going to set that equal to 0. And I'm going to solve for x, and x will equal 1/2. Okay, so I've done my second derivative, and I found where it equals 0. So if I make my sign diagram of my second derivative, notice I've gone back and labeled that sign diagram up there as my first derivative. This way I can tell which one is applying to which set of points. So this is at 1/2 here. I'm going to test a number in the second derivative below 1/2, so I'm going to test 0. So 12 times 0 is 0, minus 6 gives me a negative number. So sorry, it seems like Hudson has an itch, so you get to listen to his caller. Now I'm going to test a number above 1/2, which I'm going to test 1. So if I substitute in 1, 12 times 1 is 12, minus 6 gives me a positive number. So I have found that the second derivative equals 0 and there's a sign change. So there is a point of inflection with an x where x equals 1/2. And I would take that 1/2 and go all the way back up here to my original function to find my y value. And I already found that, and my y value becomes negative 13/2. Okay. And I can say it is concave down from negative infinity, which is down here, to 1/2. So negative infinity to 1/2. And it is concave up from that point on, so from 1/2 to positive infinity. To positive infinity. Now, these are intervals These are not points. We could have written it as when x is less than 1/2, and we could have written it as when x is greater than 1/2. We could have written it as inequalities as well. Either one of those is acceptable. All right, so looking at the second one, I'm going to draw a line because the second one becomes kind of ugly. We're going to apply the quotient rule to find the second derivative again. Okay, so in the quotient rule, my u is 6x, whose derivative is 6, and my v is x squared minus 1 quantity squared, and I have to apply the chain rule to find its derivative. So that's going to be 2 times x squared minus 1 to the first power times 2x. I'm actually going to simplify that as 4x times x squared minus 1. All right, now the second derivative comes out to be x squared minus 1 quantity squared times 6 minus 6x times 4x times x squared minus 1. Told you it was ugly. All divided by x squared minus 1 quantity squared squared. So that means this is actually now going to be to the 4th power. Okay, now this is actually the difficult part. If I was working with a calculator, I would save myself some struggle and some time, and I would take this and graph it and just simply find where it equaled 0 on the graph, meaning the x-intercept. Okay, if this is not a calculator problem, it's hard to recognize, but there is actually a common factor in both of the numerator terms and the term in the denominator. And the common factor is an x squared minus 1. So I reduce this by an x squared minus 1, and that's just x squared minus 1. And I reduce this by an x squared minus 1, and I can actually multiply those two together and get 24x squared. And I reduce the denominator by an x squared minus 1, so that's x squared minus 1 to the 3rd power. Like I said, not pretty. Let me go ahead and simplify the numerator, because in order to find where this thing equals 0, the numerator is my most important piece. So I've got a 6x squared that I'm subtracting negative 24x squared from. Actually, let me just divide out a negative 6. I'm just going to divide out a negative 6. This has a factor of negative 6. This has a factor of negative 6. Okay, let's bring a negative 6 out here. That's going to turn that into x, negative x squared plus 1, and that's going to turn that into plus 4x squared. And the reason I decided a negative 6 had to do with the fact that I wanted it out of this larger number here. So that's still x squared minus 1 quantity cubed. Simplify one more step. I've got negative 6 times 3x squared. I'm going to do some moving here. So I get a little bit more space going on. There we go. All right. All right. So 3x squared plus 1. And the denominator is still x squared minus 1 quantity cubed. All right, when this thing equals 0 will be when the numerator equals 0. So that would be at x equals, what could I put in there to make that equal 0? So 3x squared plus 1 equals 0. So 3x squared equals negative 1. So x squared equals negative 1/3. I'd have to take the square root of a negative number. No, there's no real solution here. Okay, if I do happen to, there's not going to be a sign change because there's no place that this thing actually equals 0. Okay, if I do want to look at something, I can look at where it's undefined at those asymptotes. There's going to be an asymptote at positive and negative 1, but I need it to equal 0 and also be a sign change in order for it to be a point of inflection. So there is no point of inflection here. Okay, but I can still figure out where it's concave up and concave down, because like I said, that's going to happen at -1 and 1, and those are my asymptotes, so that's why I'm putting the open circles there. Okay, so I'm going back into the second derivative, and in the second derivative, I might want to mark that so I don't forget that's what I'm looking at. Second derivative at -2. Okay, so -2 squared, that's going to be a positive number here times a negative. So that means that it's going to be a negative value here. Okay, and 0, I can put 0 in, so that's 0, that's 1, that is going to be a negative as well. Wait, I did something wrong, didn't I? 0, 0, 0. Oh, because I didn't consider the denominator. Silly me. So if I put 0 in, I have 0 plus 1, so the numerator is negative, but if I put 0 in here, the denominator is negative, which turns that into a positive number. Then if I put in the number 2, I got 12. I've got a negative number here. If I put in a 2, I've got a positive number here, so that's negative. So I can talk about concave up and concave down, but I have no point of inflection because I have no place that it equals 0. So from these negative signs, so we have negative infinity to -1 and 1 to positive infinity. We're looking at concave down. And from -1 to +1, we're concave up. So no real solution meant no inflection. That was ugly, as predicted. So we're going to come over to this side. I'm going to go ahead and draw myself a nice white box going on here, so that if I need more space, I can just go ahead and keep writing. How about that? Okay, so going back for this one, I'm going to the second derivative on this one. Okay. Oh, that's not bad. The 2 becomes 6 here, x to the first power, so it's 6x. When does that equal 0? That equals 0 when x equals 0. Okay, so at x equals 0, so we're looking for a point of inflection. It's possible because we have a 0. We just need to look for a sign change going on. So do we have a sign change? So let's look at a negative number put in here. 6 times a negative number would be a negative answer. And we put a positive number in here. 6 times a positive number would be a positive number. So in fact, we have a inflection point at 0. And when is it 0? 0 we put into the original function. 0 to the third power is just 0. Great. So we have a point of inflection at 0, 0. And we are concave down from negative infinity to 0. And we are concave up from 0 to positive infinity. Ooh, they threw a whopper in the middle there, didn't they? All right, so hopefully that helps. We're going to take a couple more examples, and do 3 examples and do them together, and then there'll be ones you do on your own.